Okay, so hello everyone for today's seminar. Today we have machine learning for CPTu interpretation and site characterization. Just to mention that this is the last seminar of this year, of this academic year. So machine learning has emerged as a powerful tool across various industries, offering valuable data-driven insights for informed decision-making. The application of machine learning methods in geotechnical engineering and soil mechanics dates back to the early 19th. However, with increased computational power, machine learning has gained substantial interest within the geotechnical engineering community and has gradually become an alternative solution for geotechnical problems. The availability of large in-situ testing databases, specifically CPTu databases, coupled with machine learning techniques, provide an opportunity to develop site-specific or regional models for various site characterization. Machine learning is also a powerful tool for investigating refinements to existing empirical CPTu relationships. With more accurate in-situ predictions of soil properties, geotechnical analysis using CPTu can be improved. This talk exposes machine learning applications in CPTu interpretation, including estimation of mine-tailing solids and fines, estimation of soil unit weight, and estimation of shear wave velocity from CPTu data. Give me one moment. No. For today's talk, we have with us Dr. Iman Entezari. He is a senior research engineer in ConeTec, leading the integration of hyperspectral sensing technology into soil and tailing characterization methodologies. With a keen interest in machine learning, he harnessed a hyperspectral vision and CPT data to develop innovative solutions for optimization, the accuracy and efficiency of soil and tailing characterizations of geotechnical site investigations. Iman received his PhD from the University of Alberta in 2016 and was a postdoctoral fellow at the University of Alberta Geotechnical Center, so right here, from 2016 to 2018. So with that, welcome back, Dr. Iman, to the center, and the podium is yours.
Thank you very much, Daniel, for the introduction, and thanks everybody for joining. So as the title of the presentation basically suggests, I'm going to go over some of the work that I've done over the past few years at ConeTec on basically leveraging from machine learning for CPT interpretation and site characterization. I'm going to go over 3 examples where we used machine learning for estimation of shear wave velocity, soil unit weight, and then basically estimation of solid content and fines content of tailings. So I'm going to get started by going over some basic concepts in machine learning. So basically, machine learning is a subfield of artificial intelligence, and it's the field of study that gives computers the ability to learn without being explicitly programmed. So we normally use machine learning on the problems that are too complicated. So it's not suited for any problem out there. ML is generally data hungry. We need to have a lot of data to be able to develop robust machine learning models and test their performance. And overall, it's an experimental procedure. We need to basically test a few approaches, test different algorithms before getting satisfying results and get the final model. So it's sort of an iterative and experimental procedure. So there are some differences between sort of a statistical modeling and machine learning modeling. I found this figure and I have put the source there. So I thought that is useful to basically bring up here. So mainly, I think the main difference is the purpose of ML versus statistical modeling. In ML, We are looking to get the most accurate predictions. So that's the final goal. We want to get the best predicted results. In statistical modeling, usually we are trying to find the relationships between the variables, and then how significant is the relationship between the variables. And then sort of the secondary goal is to develop a model so that we can do the predictions. In terms of the data sets, well, machine learning can handle big data, and it's not just the volume of data, but also the dimensionality of the data. So sometimes we have data sets with hundreds of variables, thousands or whatever. So in that case, machine learning can handle those where the statistical modeling cannot. In terms of transparency and interpretability, usually those are basically high in statistical modeling. They are transparent. We know exactly what's going on. We can easily interpret them. In machine learning, they are low, but this is an active area of research, and I'm getting into that. So there are basically works being done so that we can see what's going on and then sort of make the models interpretable and transparent. And then obviously, as I said, the predictive accuracy, normally we get high predictive accuracy with machine learning modeling. It may not be that high depending on the problem with the statistical modeling. So there are different types of learning algorithms. All the examples that I'm going to show today is based on supervised learning. So it's a type of machine learning where the algorithm learns from the label data. So meaning that we have a data set with inputs and the outputs or the labels. And then the model learns the relationships between inputs and output. And then ultimately we can basically map input to output and have a model and then use that on basically new data. So we have two main types of supervised learning, classification and regression. So classification is used when we want to assign a label, a class label or a category to new data, which is used a lot, like let's say for image classification, or I've seen papers on doing soil classification based on machine learning. And then in regression, we want to predict a continuous value or a quantity. So all the examples that I'm going to go over today are basically regression problems as we want to predict some soil properties. So in the supervised learning, the training process basically includes basically iteratively adjusting the parameters of the model to minimize the differences between predictions and actual labels. So as I said, data set has the label, the final sort of answer. So based on that, we iterate and then we adjust the model parameters so that we minimize the errors. And then finally, we evaluate the model performance using some statistical metrics like accuracy or precision for classification, or things like mean squared error or R squared for regression. So this is the overall workflow for a machine learning modeling. So obviously things start by collecting data, and then we need to prepare data. This is the step that sometimes take a lot of time. Because the data may not be organized, may not be structured, so they might be in spreadsheets. So we have to get the data, compile a data set, clean everything, make sure everything is right. And then we split the data set into training, validation, and a test set. We train the model using the training set. And then on the validation set, basically we assess the performance. And then we use the validation set to basically tune the parameters of the model, or that's sometimes called hyperparameter tuning. So once we are happy with the performance of the model on the validation set, then basically we have our test set, which is sort of this data set that has never seen during the training phase. And then we assess the performance of the final model on our test set. And that will be basically a representative of the performance of the final model. And then we deploy the model. So it could be a web-based deployment or a local deployment on our machines. And over time, basically, we can monitor the performance of the model as we get new data. And then if we realize we can add the new data into our data set and retrain the model again, that's what basically what we need to do to basically improve the performance of the model. So that's the overall workflow. So obviously, what I'm going to talk about today is the application of ML for CPT interpretation. So just going over that very quickly, CPT, or basically cone penetration test or piezo cone penetration test, so CPTu, is an instrumented push probe. So it's normally deployed at a push rate of 2 centimeters per second. And the basic parameters that we get from CPT is tip resistance, or corrected tip resistance, that we call that QT, pore pressure, or dynamic pore pressure, and then slip friction. But depending on the sensors and modules that are used for different applications, we can get a lot more data. Like if we have geophones, we can do seismic testing, or we have a gamma module that we can basically measure the gamma rays from soils or tailings or stuff like that. So depending on what sensors we have, we can measure different parameters. But these are the three basic parameters that we get from CPT. And always we know the depth. So we know these four basic parameters always. So excuse me. So the first example that I'm going to present is estimation of soil unit weight. This work has been published in GeoNiagara 2021. So we know that soil unit weight is an important soil parameter, and it's necessary to know the unit weight to basically assess in-situ stresses, like total stress, effective stress. And then we can collect undisturbed samples and do lab analysis to get the unit weight, but that's obviously costly and time consuming, and it's challenging to collect undisturbed samples. So empirical relationships have been developed to estimate unit weight from CPT. Those are mostly based on limited data sets and say statistical modeling. So in this work, we wanted to see basically what happens when we adopt a machine learning approach and if we get better results or not. So the data set that was used in this study is the same data set as used by Dr. Paul Meng at Georgia Tech, updated with new data. So if you look into that paper, you basically see this figure that using that data set, Paul has basically developed a correlation to estimate unit weight based on slip friction. So we use this same data set, and then we applied machine learning to see what we get. So the data set included more than 1,200 paired CPT and lab measured unit weights from soil samples. The soil samples were from 114 field test sites with a variety of soil types, geological environment, and stress stories. And the soil types included peat, clay, silt, sand, etc. The CPT parameters that we had included basically tip resistance, dynamic pore water pressure, slip friction. For this data set, we had hydrostatic pore water pressure, or U0. Effective stress was also available, and then we have the depth for the CPTs and obviously samples. So in this basically histogram here, you see the histogram of the training set in blue and test set. So basically, we got the data set. We took 20% of that as the test set, and then used 80% of the data set as our training set. And then basically, we used a machine learning algorithm called random forest, which is widely used for classification and regression tasks. It's basically an aggregation of decision trees, as you see in this diagram here. So we train multiple decision trees. And then in case of regression analysis, we take the average of the predictions from those independent or individual decision trees. And then that average value is basically our final prediction. So we developed a couple of models. The first model that we tried was using basically QT, FS, U2 depth, U0, and effective stress as basically 6 parameters, 6 input variables to estimate unit weight. So here you see measured versus estimated unit weight. So the correlation is high, R squared is 0.86. And this is the cumulative distribution function of errors. So basically the value of the at the 50th percentile can be considered as the bias of the prediction. So it's near zero, meaning that the model is not over or under predicting. And then the values at 16 and 84 percentile could be considered as plus minus 1 standard deviation. So we took the average of these two values as the final error, which is basically the error with sort of 68% confidence interval band. So the issue with this model is that obviously, well, we may not know U naught always. And then effective stress, in order to have effective stress, we actually need to know unit weight to calculate total stress and then calculate effective stress. So we might do some repetition or iteration to basically be able to use effective stress as a parameter. So then in next step, we just try to see what happens if we just use the 4 basic CPTu parameters. And this is the results we got. So obviously the performance decreased a little bit, but it is still a strong correlation with overall error of 0.93 kilonewton per cubic meter of soil for unit weight. So we basically developed some other models based on different combination of input variables. But ultimately, like random forest number 3, which is the model that I showed in the previous slide, uses the 4 basic parameters from CPTu, which we always have. So this is the model that basically is our final model. And then we took that and compared the results of this one with some of the existing relationships. So these are some of the widely used CPT-based relationships to estimate unit weight. This one by Robertson and Cabal 2010. So we have the equation, and then here's the performance of basically this model on our test set, the same test set that we tested the performance of the machine learning models. This is Main 2010. So you have the equation here. Effective stress is a parameter in this model. So here's the performance we get. Main 2014. The same data set that actually we used in this machine learning development work. So here's the performance of that model on our test set. And this is another one by LinGeek et al. In 2018. And that's the performance of that model. And then here's sort of a comparison between some of those widely used relationships and machine learning ones. And obviously, as we can see, generally, the R-squared bias and error for the machine learning models were better than those existing relationships. So one of the issues is that with those existing relationships, there's an equation, it could be published, everybody could use. With machine learning, so obviously the equation is not a simple equation, but it can still be used as, you know, in our softwares, we can basically have standalone packages or basically incorporate those into software or make them available through web so that people could use. But obviously, there is no simple equation that could be included in papers for basically for being used by practitioners. So one of the issues with machine learning modeling is basically interpretation of the models. So we did some work, and this is called SHAP analysis. So I have put the links here so you can go read about SHAP analysis. So basically that's based on game theory. So basically it explains the output of any machine learning model. So the plot that I'm showing here is called a force plot. So that shows how each feature for specific measurements with these values, how the model works to get to the final prediction. So there is a base value for each model, which is basically the average of all the, let's say this is the unit weight model. So this is the average of all the unit weight in our training set. So that's called the base value. And then this plot shows how each feature contributed to get to the final value, which is 18.17 for the unit weight. So it basically tells us that how U2 depth, sleeve, and then tip resistant each contributed to the model to get to this value. So if you do this analysis on the entire test set, we get a plot like this. So this tells us QT is the most important parameter, because as you can see, it has the most impact on the results, followed by friction ratio, and then dynamic pore water pressure and the depth, which is sort of interesting because most of the models out there are based on QT and FS. So these are the ones that have sort of high correlation between to have high correlation to unit weight. And it was interesting to see that machine learning also picked those ones. And those are the most important basically features to the model. So this kind of work is interesting because machine learning is usually known to be sort of a black box thing. So using analysis something, well, people call that to go from black box to white box or glass box, basically. So we have some sense of what's going on under the hood and what's which feature contributes the most and things like that. So I'm gonna basically present on that in the next example as well. So switching to the next topic, which is estimation of shear wave velocity. So part of this work has been published in CPT 2022. And then the second part, which is an update, will be published in ISC 7 in June of this year, basically. So this work, basically, we try to see what machine learning basically, or if we can develop a machine learning based model to get better performance for the prediction of shear wave velocity. So measuring shear wave velocity is normally done using seismic CPT. But again, there has been a number of relationships to estimate shear wave velocity from CPT data. And then again, we wanted to see what happens with machine learning approach. So in order to compile our data set, we basically looked into the seismic CPT data that we have collected over the years. So when we have seismic CPT data, we measure shear wave velocity or VS over certain depth intervals, normally 1 meter depth intervals. So we have a profile like this. So the way we compiled our data set was to take the average of QT, FS, U2, that basically corresponds to that, say, 1 meter layer. And then this way we built a large data set of paired CPT data with basically shear wave velocity. So the data set includes more than 180,000 paired VS and CPTu data. These are from more than 10,000 independent seismic CPT soundings worldwide. So this heat map here sort of represent where the data comes from. So most of the data is from Canada and the US, and then from South America, but we have contributions from, say, Australia and other parts of the world. So this basically shows so we basically split the data set into training and test set. And this basically was done based on the year that the data was collected. So we took the data collected between 2017 to 21 as our training set, and then the data from 2020 to early 2023 as our test set. So this way we could have an unbiased performance assessment. And then this shows the test set on the normalized tip resistance versus I sub G, or small strain rigidity index. So it's been proposed by Dr. Robertson that a empirical value of a KGSR, which is an empirical value. So KGSR of 330 could be basically sort of a threshold to basically tell us if we are in cemented or uncemented soils. So this is not sort of a hard threshold. Obviously, this is a spectrum. So if we have higher KGSR, it means that the soil is more cemented. If we have lower KGSR, it means that it's more on the uncemented or ideal soil. There is no microstructure. So, but the value of 330 is a value that is sort of a cutoff to basically classify things to cemented and uncemented. So this is important because most of the relationships that are developed for CPT interpretation are for uncemented soils. So we wanted to see what happens if we look into uncemented and cemented soils. So that's why we basically split the data set based on cementation status. So for this work, we used XGBoost, which is another widely used machine learning models. We developed 3 models, one for all soils. So we used the entire training set to develop that model. We used the model for uncemented soils. So we only used the uncemented fraction of the data set to train the model for uncemented soils. And then obviously the cemented fraction of the training set to develop the model for cemented soils. And these are the performance of the models on the test set. So this test set was not used in training, obviously. So we see how different models performed on for all soils, uncemented and cemented soils. And these models were developed based on these 4 basic CPT parameters. We also applied Main 2006 and Robertson 2009 on the same data set. So again, these models have been developed for uncemented soils. So it's fair to look into uncemented soil fraction of the data set of our test set and then see how they perform. So here's the performance of those 2 models. I have a table later on that basically shows the errors and everything. But we just recently did an update, and that was to see or to explore what happens if we include the latitude and longitude of the data into the model. So the top ones show the performance of the models that I showed in like the previous or 2 slides ago, which is the models just based on QTFSU depth. Then we included latitude and longitude or geographical location of the data into the model. And then we wanted to see what happens. So we noticed some sort of like marginal improvement, like overall, like if we look into the uncemented soils, it's obvious that for some parts over here that the model without latitude, longitude, we have sort of some outliers or higher errors here, but we get better performance once we included the latitude and longitude. There are some basically points or there are some considerations here. So obviously we can only use the models with latitude, longitude if we are performing the testing in the areas that we know that we've been there in the past, basically, and we have had training data or data in our training set from that specific location in our data set. Otherwise, if we go to a new location, which we have never done testing, it doesn't make sense to use the model with latitude, longitude. So these are some of the like research stuff that we've been trying to explore and then see what happens. Then this is just like the overall performance of the models, just with basic CPTu models with latitude, longitude, and then those 2 widely used models. So obviously, like one question here is that, like, how do we know if we are in uncemented or cemented soils? That's sort of important. If we don't know, we probably need to use just the all soils model. But if there is some information from the previous testing, or if we know some info based on some geological testing or things like that, we know if we are in cemented or uncemented soils, then we can use those specific models that were developed for cemented or uncemented soils. So we again try to do some SHAP analysis. So for the uncemented models, so the model with just basic CPT, here's the feature importance basically. So depth was the most important feature, followed by QT, FS, and U2. And then for the model, the uncemented soil model with the inclusion of latitude, longitude, it was depth, followed by QT, and then latitude, and then FS, and then a little bit of contribution from U2 and longitude. So we tried to dig into that a little bit more, and we looked into something called partial dependence plots. So these plots basically show the impact of a single variable on model predictions. holding other variables constant. So let's say this top plot here shows how the estimated VS results change if we just change the depth or Z here, and then keep basically all the other parameters constant. And these are the results for the models that we included latitude and longitude into the model. So those sort of thin gray lines are just a few examples, and it shows how just by changing the depth of those instances, how the predicted values change. So we can see overall, there is a sort of positive correlation between depth and estimated VS. As we go deeper, the estimated VS results increases. But then we did that also for latitude, longitude to see what we learned. So those seem to be a little bit more complex. There is no, say, universal correlation between those. But we noticed, like, for this specific area here around latitude of -16, we noticed that the estimated results are generally higher. And overall for longitude, it seems like the relationship is sort of flat. Longitude doesn't contribute much. But it's important to note these are specific to our data set. So we cannot make a generalized conclusion about the latitude and longitude and their impact on the VS result. These are specific to our data set. So we looked a little bit further into what's going on in this region. And then we noticed in this region, we have deep water tables. And then deep water table basically means a higher effective stress. So we thought, okay, that makes sense that for these regions, we have higher estimation of VS results because we know that effective stress and basically VS are sort of correlated. So then we looked at the depth and shaft values, which is the impact of the model based on basically on the predicted results for depth. And it was interesting to see, so these sort of orange or highlighted points are the location, are basically the data from the location that is near this region with -16 latitude. And then it sort of makes sense that for this region, depth contributes more to the predicted results based on the fact that we have a deeper water table and higher effective stress. So these are all examples to show how we can sort of interpret machine learning results. Okay, and this is just a profile showing how the actual measurements compares to machine learning models. And then again, those two widely used correlations out there. So the last example is basically estimation of tailings constituents. We have published a couple of papers on this topic. This is specific to oil sands in Fort McMurray. So we know that each year we collect thousands of samples, or mine operators basically need thousands of samples. The samples get shipped into the labs for analysis, and then basically they measure a bunch of tailings properties like solid content, fines content, MBI, which is an index testing, and things like that. This is basically a costly and time-consuming process because we need to do sampling and ship it to the lab. It takes weeks to get the lab results back, and then we wanted to see if we can develop a model to basically estimate those lab properties from the CPT data. So these models are, some of the mine operators are actually using these models, the tailings behavior type models, and they heavily rely on that in reporting. So I'm going to go over how basically this was done. So in the oil sands, we normally push gamma CPT. So gamma is a module that basically measures counts per seconds of natural gamma rays that are occurring from the radioisotopes of potassium, thorium, and uranium. So in soils or tailings that contain elite clays, we have seen that gamma counts are related to the clay content and fine content. So there is a high correlation between gamma and fines content in the oil sands. So if we look into a gamma CPT profile, so this is a profile that basically goes from the recycled water to FFT or fluid fine tailings and into soil-like material. And then if you look at this last box here, we see the gamma measurements, which is basically the continuous black line. And then the circles are the lab measured fines. And as you can see, there is generally a good agreement between gamma and fines, and that's why gamma CPT is very useful in oil sands tailings. It also, there is other applications for that as well, but for now, I'm going to skip that. So the way we put the data set together and compile the data set was using our geotechnical database. So basically, the thing is that we queried our geospatial database and we found basically pairs of gamma CPT and lab results. So in oil sands, we've had the luxury of sort of getting the lab results from our basically oil sands operators, from the oil sands operators up in Fort Mac. They've been collaborating with us. They've been sharing the lab results with us. So that's how we've been able to do the modeling here. So we found the gamma CPTs and the nearby samples and sample results. So the pairs were selected from all the oil sand region, all the ponds that we had. And then we paired those basically gamma CPT with lab results if they were within a 5-meter radius of each other and if they were basically collected within 1 month of each other. So this is basically showing how the pairing happens. So if we have samples, so we normally have 2 types of samples, fluid samples and then sonic samples. So for fluid samples, we took the average of CPT or gamma CPT data over a 0.5 meter window size centered at the elevation of the fluid sample. And then for sonic samples, we took the average of those CPT parameters over the length of the core sample. And then we push cone or ball basically in oil sands. So the model works. We basically developed a model in a way that works on both cone and ball data. And then once we did the pairing, so now we know the CPT data, and then we have solids, fines, and MDI from the lab analysis. And those are the 3 parameters that we try to basically estimate using a machine learning-based model and then gamma CPT data. So this shows some overall characteristics of the data set. So we had a total of, I think that's the number. Like we have like 17,000 basically paired gamma CPT and lab results. And then you see the characteristic of the data set in terms of solid content, geotechnical fines, and fines over fines plus water. This is a ternary diagram that is that has been proposed by COSIA, and then basically shows the classification of the points based on the system that they have proposed. And these are the histogram of the training set for solids content, total fines, and MBI. And these are the 3 parameters that we try to predict with gamma CPT and machine learning. So our training data included the data collected in 2011 to 2019, which was roughly 85% of the data set. The test set included the data collected in 2020 and 2021. So that's our test set again. So we wanted to do an unbiased performance assessment. So that's why basically splitting the data set based on year is an ideal way to do this split. And then this is sort of a class A or blind evaluation of the model, because obviously the data in the test set was basically collected in years that was not included in the training set. So we looked into some of the relationships between, say, some of the CPT and those lab results. So this one shows solids versus slope of dynamic pore water pressure. So normally a very high correlation between that in particular in fluid tailings. In non-fluid tailings, we cannot calculate the slope, so there is no relationship between slope and solids. This shows the relationship between total fines and gamma. So generally high correlation. And then we also looked into some of the sort of just correlations between lab results. And then like this one shows geotechnical fines, which is fraction of fines to the solids. And then MBI, as I said, is that it's an index testing that is then used to sort of estimate the clay content of tailings. So we looked into that, and then we ultimately decided to do some screening based on the relationship that we saw here. Like so for some of the data, the relationship didn't basically follow the pattern of the sort of the positive correlation between the two. So we did some screening based on some data exploration. And then ultimately we used deep learning or neural networks to basically develop the models. The input parameters for these models, or for this model, was tip resistance or scaled net tip resistance for basically undrained shear strength, which can be calculated for both CPT and ball data. Slope of dynamic pore pressure, linearity of dynamic pore pressure was also a feature in the model, gamma counts. And then we also use mining property name as a feature. So this is sort of a categorical variable. And then because each operator uses a different lab, we mostly use the mining operator name as a property into the model as a proxy of the lab, and then basically the variation that exists between labs. So neural networks, so these are our input features. And then basically the output is three basically tailings properties, including solids, fines, and MBI. And then we did sort of a bootstrap aggregation. So basically meaning that we split the training set into multiple training sets. We developed neural networks basically trained neural networks using each of those training sets. And then we sort of aggregated the results, and it's been shown that the bootstrap aggregation basically improves the robustness and generalization of the model. So this is the performance of TBT, or those machine learning based models, for solids, total fines, and MBI. So you see the lab results on the x-axis, and then the predicted results using neural networks on the y-axis. And then these are the distribution of errors, and then ultimately the overall error for estimation of solids, fines, and MBI. So this was an example of doing sort of site-specific modeling, or in this case, region-specific. So this is obviously, as I said, this is just a model that works for oil sands tailings. This model cannot be used anywhere else. But the same methodology could be applied on other mine waste, tailings, or basically soils, to have a paired CPT and lab database, and then see what sort of models we can develop. And this is the table that basically summarizes the errors for measurement of those tailings properties, the overall performance of the models, and then based on, like, we also did error assessment for each individual mine or mine operator. And then also based on gamma CPT or gamma ball data. And then ultimately, these are some of the TBT profiles. So in these plots, like blue, the continuous line is the estimated results using the TBT or the machine learning based approach. For solids, red is for total fines and green is for MBI, and those circles are the lab results. So pretty good agreement between the predicted and the lab results in fluid fine tailings. This one is in soil-like material with high solids, low fines. This one is layer deposit. So one of the advantages of sort of this type of work is that when we do sampling, we may miss those thin layers, but with a continuous profile like what we get from TBT, we can have a better resolution. And then this is an example with gamma ball data. So as I said, the model works for both, or works on both gamma ball and gamma CPT data. Okay, so in summary, so I tried to go over some of the examples of how we can leverage from machine learning and CPT data to basically enhance some of the existing relationships or develop new models or site-specific models for better site characterization. So in geotechnical engineering, we frequently use empirical relationships to estimate soil parameters. So therefore, we can benefit from ML. The availability of large testing databases, specifically CPT databases, coupled with lab results and ML techniques, basically provide an opportunity to develop site-specific models for better site characterization. So as I basically explained, ML could be a powerful tool to investigate refinements to existing empirical CPT-based relationships. Obviously, for a lot of projects, we still need to do drilling and sampling and do lab analysis. But we can still use ML-based CPT models to basically add value to the basically basic CPT parameters and have more cost-effective and rapid means to provide some extra information. And then this is the point that we also want to basically say and include, and that is that geotechnical community is encouraged to create high quality and well-structured geospatial databases of in-situ and lab results, and that way basically we could then apply the machine learning and new emerging models to have better site investigation tools. And with that, thank you very much. And I think the floor is open for questions.
Okay, thank you very much, Dr. Entezari. Yeah, now we have the time for the questions. There is any question here in the room? Okay, so for the people that is online, you can raise your hand or you can just type your question in the chat, whatever you prefer. Where is my mouse?
Okay, no questions, easy audience.
Okay, we get our first question. It says, well, we get multiple questions now. People are just taking time to write. Okay, first question. Can you elaborate on how the performance of the ML models were compared against the empirical correlation? Say for unit weight, what does the R-square value for rubber and cobalt represent?
So I think that was go back to this slide on unit weight. So these are again some of the widely used correlations or equations for unit weight, and this is how they performed on our test set. So this is the R-square of the Robertson and Cabal method, and then say main 2010 and 2014. And in this table basically compares basically machine learning models and those existing relationships. So the machine learning model overall performed better, like even the model with just basic CPT parameters that we always have had higher R-squared, 0.81 compared to say 0.60 for those existing relationships, and then lower bias and error overall. Does that answer the question?
I don't know. I wasn't. Okay, now there's other question. I mean, we have multiple questions. This one is, from Shear. It says, what are the accuracy level considered to be good interpretation using ML?
What the accuracy level considered to be? Well, I mean, it depends. Like it depends, I think, on the application and what you want to achieve. A lot of time, it's the end user that needs to make a decision. So basically, when we do the machine learning modeling, we do all the experiments, we try different models, and ultimately we provide a final error assessment on a test set. But I think that's up to the end user to decide whether that error is good enough for their application or not. And then if they want to use that in their design, do they need to increase their risk or safety factor or whatever. So it's up to the end user to say, okay, this is good enough. If say, like let's say in TBT modeling, what we did was that ultimately we observed roughly 5% error for estimation of solids. And that seems to be good enough for a lot of applications. But I mean, in some cases, you may realize, okay, even with machine learning models and all the data you've had before, you are not getting the results that you were initially interested in. And that shows basically you cannot use any modeling, and you have to have other means of either lab testing or other sort of in-situ testing to get the parameters that you are interested in.
Okay, perfect. For the people asking about sharing the slices, we are going even to upload this video in the YouTube channel. So you are in the YouTube channel of the Geotechnical Center of the University of Alberta. So if you go to YouTube and look for that, you will find most of our talks right there. So next question is from Peter Robertson. It says, Robertson and Cabal include soil-specific gravity. Have you considered included the specific gravity in the machine learning?
That's a very good point. No, we haven't tried that, but that's a great point. We have to see what happens if we can have that and then include that in our model. Good question.
I guess those are all the questions we have for today. So again, thank you very much, Dr. Entezari, and thanks everyone for joining our sessions during this academic year. See you next fall.
All right. Thank you so much.